Well, actually, most of them are from pre-calc. One of them isn't. Right? Well, and that may or may not be true. That last one, you may have seen it in pre-calc, but I don't have the expectation that you would have remembered it. All right. So the first one is really actually algebra 2, maybe even algebra 1. This is keep the base, add the exponents. Right. This is Lagrange, or the Venn relationship, if you like that one. I tend to gravitate towards the Venn one, but maybe you like Lagrange. Actually, that's not even remotely true. I don't use either of them. I use circular motion to convert from logs to exponentials. So if I had something like, I don't know, let's say we have log base 2 of x equals 3. Well, the base of a log and the base of an exponential, the term is the same for a reason. That serves as the base of our exponential function. And then I work around in circular fashion. Base, power, result. So as long as you know where the particular items are supposed to go, you could always just kind of go around in the circle and go from there. What some people have said in the past is that they know that this is the base of the log, so it's the base of the exponential, and these two guys get swapped. And that gets them from log to exponential form. It also works to get you the other way. So the mnemonic device Lagrange has DNA, or the Venn best number ever relationship. I don't know that you necessarily need that, but if you like those, then go with it. The next one down the line is change base formula. So it's in general terms, but if you have something like, for example, log base 2 of 3, that would correspond, I generally want to change my base into natural logs. So I would say ln of 3 over ln of 2. You may not have experienced too much with that because a lot of our calculators can actually work with bases other than e or 10. So you might have just used the log base function in the past. But for our purposes, when we start getting into derivatives of logs, it's much easier to work with natural logs than it is to work with other types of logs. So doing that conversion is not the worst idea at all. The new piece of information right now is the limit as a approaches 0 of e to the a minus 1 over a equals 1. Not something that I can prove just yet because we need to learn more about derivatives in order to make that happen. But once we do, I can come back and show you why algebraically or analytically that actually ends up equaling 1. Right? But for now, we can determine that if I were to directly substitute a 0 in for a, I would get e to the 0, which is 1. 1 minus 1 is 0. So 0 over 0. All we know at this point is that 0 over 0 tells me I can get an answer. I just have to do something in order to make it happen. The issue here is we don't know what to do in order to make that happen yet. But we will, and it'll be exciting and interesting when it happens. All right, so in number 1, we're going to go back to the limit definition. We're going to use the traditional one. Limit as h approaches 0 of e to the x plus h minus e to the x all over h. All right, so if I didn't talk about any of those properties there, or at least consider any of those properties, I might look at this and say, I don't know what to do. Do I try to cancel the h? I don't know. But there's actually something very meaningful that we can do, and it involves this expression here. I'm going to make sure I have the relevant key sign. So the e to the x plus h, I would be looking at that using the first rule that I have up here. So e to the x plus h could also be written as what?
E to the x times e to the h.
Beautiful. perfecto. Yeah, you're just working backwards. So e to the x plus h would correspond to this. So basically, you had a situation where you kept the base and add the exponents. You're just undoing it. All right. So just rip it. Cool. You want scissors?
Oh, I got it.
Oh, okay.
Yep.
Yeah, I've had those cases in the past where, you know, there's a person opening a can of soda, but they're trying to be like polite about it, so they think opening it slowly is gonna do the trick, but that just makes it worse, because instead of having a one loud, it's sorry. For like the next 5 minutes, so yeah, just rip the band, just go for it. So once you have it in this form, hopefully it's pretty easy to see that there's a common e to the x. I'm going to take that out of the entire limit. Using mathematical magic. No, it's not related to the limit. It doesn't have an h in it, so it doesn't need to be there. All right, so always keep that in mind. The limit is as h approaches 0. If there's no h in a particular factor, it does not need to be in the limit at all. All right, it's kind of like what we did yesterday with the with factoring out a cosine from the entire
Where'd you
thing.
get the minus 1 from again?
Oh, GCF. So I divided each term by e to the x.
Why can't you just... Oh. Yeah.
All right.
I see it.
All right. So then what is this one equivalent to? 1. So we're looking at e to the x times a 1, which is just e to the x. And I would say that this is probably the most interesting. I'm going to say dy dx. Again, that's other notation for saying derivative. I have y equals, so the derivative of y with respect to x, the derivative is equal to e to the x. This is, I think, the most fascinating out of all of the types of functions, because to try to conceptualize how on earth a function can be its own derivative, like, in order to really conceptualize that, you got to start thinking about, again, what a derivative is, which is what, again? What is a derivative? Slope of a tangent line, right? So what that's telling me is that at any point for x, the slope will be the function itself. So its rate of change is whatever the y value is at any particular x. So to try to contextualize that's we're not there yet, but we'll try to be, because to think of a rate of change as just some function in and of itself is already challenging enough. But then to think about how on earth this could, you know, even first of all happen, and then what that means in the context of the situation, that's like otherworldly at this point. But we'll get there. All right, right now we're just kind of getting the skill down. All right, so then when you look at the remaining problems, you see that they're all kind of variations of this idea. Now, I don't know. I feel like doing number 2 with the limit definition would be kind of beating a dead horse, because it's a constant multiplier of e to the x. All right, so that's why it's using the limit definition and or properties of exponential and logarithmic functions. So we wouldn't want to start off with the limit definition on this one, because we already know what the derivative of e to the x is. And the constant multiple rule tells us that if I want the derivative that all I have to do is just hang on to whatever my constant multiplier is, and then take the derivative of the parent function, which we already know is e to the x. Not that simple. 3 e to the x would be my derivative. All right, so that's not bad, provided you have this information. Right? And I think personally, I mean, you compare this to like derivative of secant that we did on the previous page, or even a cosine function. This is much quicker and easier, but it requires you to know this piece of information. Right? For number 3, we have f prime. I'm kind of mixing up notation on the fly here, just based on what's presented to me. Previously it was y equals, so I went with dy dx. Now it's f of x, so I'm going with f prime. You can alternate back and forth if you want.
For one of the ones with y, if we use like f prime on a test, would you take points off? Or?
No, it's perfectly fine. Yeah. I mean, we're going to switch up at some point and work with functions that are in terms of y. In that case, you want to be careful about notation, but if it's in terms of x, it'll be fine either way.
Why, for those limit definitions, didn't you use x minus a?
Because it doesn't work as conveniently
Okay.
as it does in this context.
Is that like a skill we're gonna have to know?
The x minus a stuff for this?
Like choosing which one?
Oh, notation.
Yeah.
Not. Yes and no. I mean, I would say knowing when one method is appropriate as opposed to another is probably a good skill to have. But really, it's kind of coming out the way as we've been progressing through the unit. It's kind of been the idea has been emerging that once you start getting away from algebraic situations, you sort of start getting away from the alternate difference quotient. So trig, exponential, logarithmic functions, we start going back more towards the traditional method. All right, and so that seems to be a recurring theme. So anyway, when you have a sum or difference within an expression, we can take the derivative of each part separately. So if you're armed with that piece of information, I know that this part is going to have a derivative of e to the x. What about the other one? What's the derivative of negative 3x to the 6th?
18x to the 5th.
Negative 18x to the 5th. All right, so that's just the power rule. All right, we discovered that a couple classes ago. Multiply the power by the coefficient. That's your negative 18. Reduce the power by 1. All right. This would actually be pretty nightmarish if you had to do it with a limit definition. Because you have a power of 6 in there. That would be pretty crazy. All right. But then we come across something like number 4. And number 4 is a little bit iffy. Actually, we get into the iffy category with numbers 4, 5, and 6. So for this one specifically, we have a function contained within another function. We're not there yet in terms of how you would handle it in the current form. Ooh, that's good to know. You're gonna have to check that video out later. Yeah, my theory is that XS is a villain.
Oh, really?
Secretly, yeah. So, and I think she's a twin.
Oh, you do?
Yeah, I think they're going to Dawn and Don, but I think that it's 2 female twins, and
Really? So it'll be like Dawn is the other twin,
or some playoff of Nora, maybe.
Oh.
But the
I'm sorry. I love the Flash.
and but I was talking to my son with this for like an hour after his bedtime last night, so I got into a lot of trouble with that.
I love Nora too much. I love.
But I think what happened last season is anytime that there was a subtle difference in their appearance, I think we were seeing the twin.
Oh.
And
This
so.
is like really crazy to watch, not knowing
Anything,
Oh.
anything about it? So a child traveled back from the future. Does that clear things up?
Pretty much, yeah.
She might have a twin, but maybe not. It's unclear. No one knows.
And she messed with the timeline, creating a new villain
Called
who
Cicada, because he sounds like a
So-
bug.
he does.
I have a question. So why is it minus 18x?
Way to take
Oh,
it,
Bill, yeah.
Roy.
Twice.
Power rule.
I'd be
6 times
disappointed if
negative
this
3.
doesn't make it onto the YouTube video.
Oh yeah, that is
And then reduce the
That's
power
what
by
I was
1.
whispering.
So you got to flip back like 5 pages in your packet. cover a class tomorrow. Okay, so we have to take this one from scratch because we don't know what the impact is going to be of that 3. So let's discover it. The limit as h approaches 0 of e to the 3 times x plus h minus e to the 3x over h. All right. I'm going to distribute the 3. Let me just bring it in a little bit. Like this. So limit as h approaches 0 of e to the 3x plus 3h minus e to the 3x all over h.
And then is it just like the same thing as the first one where it's like e to 3x times e to the 3h?
Exactly. All right. I can factor out the e to the 3x. And at first glance, you might think that this is just another clean cancellation of the limit, but it's not, because that denominator needs to be what? 3h. So let's do a little correction here. Multiply the bottom by 3 and the top by 3. Now I could do my cancellation. That goes to 1. And so we end up with 3e to the 3x as my f prime. All right, so it seems kind of like what happened with the trig situation, where whatever the coefficient was of x in your exponent, that ends up being the coefficient of your derivative.
When you just like crossed out that entire thing, like I lost it. Like how'd you get your answer from there to?
Yeah.
Okay.
That's the
Oh, and then you multiply the 1 by the outside 3. Okay.
Why do you need to multiply it by 3?
Because the model tells us that whatever's in the exponent has to match the denominator.
Okay.
Here it was 3h and just an h. I needed it to become a 3h. Okay, so the coefficient of x, that seems to be the important piece here. Same thing with the trig situations. Okay, so what does that coefficient represent? If it was just an equation y equals 3x, what would the 3 represent? Y equals 3, yeah, I think I heard it. Slope. Y equals 3x, this is the slope, right? So if I'm talking about something like, and I'll write it in the simpler form, f of x equals e to the x, well, I'll write it this way first, which became e to the 3x, because you do have to make that transition first before you can really consider it. What you're looking at here is e raised to a power, but that power is another function. That's why you learned about composite functions back in Algebra 2, a function within another function. So that function itself is y equals 3x, the slope of which is equal to 3. Right? So what we're getting at from this whole idea, and this is where all the puzzle pieces start to fit together, is going back and thinking about those trig situations. We had something like y equals the sine of 2x. That 2 was the slope of the line y equals 2x. all right, when you had cosine of 5x, that 5 was the slope of the line y equals 5x. Here, the 3 is the slope of the line y equals 3x. So it seems to be the case that what we're doing is taking the derivative of the function the way we normally would, but then multiplying by the slope of whatever the inner function is. All right, so in this case, whatever is in the exponent. In the case of trig, whatever was contained within the sine or cosine or whatever. All right, so we can apply that information because in the very next problem, rather than actually going through the limit process again, it seems that all I need to do is reproduce what I have here, e to the 3x minus 2, but then just multiply by whatever the slope is contained within the exponent. All right, so if this were the equation y equals 3x minus 2, what would be the slope of that line? 3. And so we have at least what we would suspect to be the derivative. Now, if you want, you can go through the process with the limit approach, but I would recommend, instead of doing that, try using your calculator to verify your answer. Right? Because, I mean, the whole point behind it is for us to learn what the relationships are using the limit approach so that we don't always have to use the limit approach, right? So if you have your calculator set up the right way, aka you've been paying attention, then you're going to be in good shape. But just in case you weren't, I'll help you set it up one more time. Also, on the off chance that maybe you did do it, you were paying attention, but then you loaned your calculator to somebody and they didn't like it, so they cleared it. Or you're in another class and they told you to clear your calculator before a test. Or you were just absent. That's actually probably the most likely one. So in y1, I would want to put my original function, e to the 3x minus 2. In y2, I'd want to put what I think the derivative is, 3 e to the 3x minus 2. If you're going the visual route, meaning you're not looking at the table, then you want to turn off your y1. So again, to do that, you just hit enter on the equal sign. So it's off. If the equal sign is bolded, the equation's on, meaning it'll show up in a graph. If it's not bolded, it's off, meaning it will not show up in a graph. y4 is where we're going to have the calculator determine the derivative. So math, option 8, pop in an x, pop in a y1, alpha trace y1, and then an x again. Again, for most of us that's already there, but for some of us it's not.
Wait.
Alpha trace y1. And then I'm going to hit enter on the slashy thing.
My first one is on too, so I'll be
You want the first one to be off. We only want y2 and y4 off. So what I think the derivative is, I want to see that. And I also want to see what the calculator thinks the derivative of y1 is. But I don't want to see y1 itself. All right, assume 6. Hopefully that's a good enough zoom. It seems to be. If the second graph traces on top of the first one, then we know we did it right. There it is. All right. It seemed like the second one had a whole lot of negative x values that maybe the first one didn't have, but that was only because the first graph was so close to the x-axis that it was indistinguishable. And because this one came in as bold, you were actually able to see it. So that's confirming it. You can look at the table, also second graph, but that's not as satisfying. That moment of pause, the anticipation of like, will it not? I don't know. That excitement that's added to it only comes from the graph.
I don't know why it didn't work.
light. Or hit on first intro.
Where?
On. You want to turn Y1 off. All right, so at a minimum, you have a way of checking your work. Some questions, this is enough to actually solve a problem. You know, like a multiple choice question, which, you know, it's not, doesn't happen often, but sometimes I like to throw them in. Which of the following is a derivative? Oh, you could use this approach. You don't even have to do, you don't even have to know shortcuts for that. You can just use a calculator. I like to reward calculator use. All right, and so what that means is the first time I explain something, you know, related to the calculator, it's hit or miss as to whether or not people are paying attention. Then as the year goes on, people realize more and more that it's advantageous to pay attention. And sometimes it's too little too late because, you know, while we're working on more advanced things, you're still trying to figure out how to get a Y1. Meanwhile, most people have become very familiar with that. But yeah, on a test, I mean, the reminder will be there, but it's basically something along the lines of, you have a calculator, so use it. The directions, if they don't tell you to do something analytically, the last test, a lot of the questions said you had to do it by hand, basically. But moving forward, if it doesn't say you have to do it analytically, you don't have to do it analytically. So if I were to say, find the derivative when x is equal to 2, if I don't say only an analytic approach will be accepted, you could use your calculator, just give me the answer and walk away. Right? And so what's going to happen is some folks will get mad because at the end of the test, with 10 questions, you'll be on question number 3, upset that you don't have enough time to finish, wondering why like 90% of the class has already been done for 20 minutes, and you're trying to figure out how that happened. It's because they listened, started using the calculator appropriately. You didn't. You tried doing everything by hand, and you didn't finish the test. All right, so that's going to be an issue for some of you. It always is, but hopefully me bringing this to your attention will keep it from happening too frequently. All right. Now, number 6 is a little bit of a different story because it's not a base E. So then the question becomes, all right, well, what do I do? You could actually do a lot of good things here, but what we want to do is make it a base E. So to sort of cut to the chase, I guess, let's at least focus on that. So I want the 2 to be an E. All right, so what I'm basically saying here is that E to some power, I don't know what the power is, that's kind of the point, is going to be equal to 2. Because what I want to be able to do is take this expression, write it as y equals e to that, whatever that power is, to the x. And then go from there. I'll show you what that looks like in a few minutes. But I need to figure out what this power is in order to make the equivalent relationship. All right, so I'm going to come up with a dummy variable. So anything other than x or y. It really doesn't make a difference. N, I guess. I need to solve this for n. All right, so that's where the whole log or Dan business comes into play, if you like that sort of thing. I know that the base of an exponential and the base of a log are always the same. And then I could just do the switcheroo. Swap the n with the 2, and I'll have my equivalent log expression. So 2 and n. And I like to check it with the circular motion. So base of e, so e to the n equals 2. All right. A log base e is what kind of log? Natural log. A log natural. All right. So the n value that makes e, well, so whatever e raised to the power, and we wanted it to be equal to 2, the n that makes that work is somehow equal to the natural log of 2. All right? And this is actually a property from pre-calc that was gone over. Its relevance was maybe discussed, but you never really did anything with it. And it was like, all right, well, here's another rule. You're like, what do we use this rule for? No, you're probably using calculus or something. So here we are. So these are two inverse functions. If you take the inverse and substitute it into a function, the result is always whatever is contained within the inner function. So they call it the argument, right? Long story short, it's telling me that the e and the ln cancel out and just give us a 2 as a result. You can verify it in your calculator. You could also go the other way if you wanted. Ln of e to the second. This one might be a little bit more obvious because you have a log property that'll get you that. But basically, e and ln cancel each other out. All right? So that's telling me that if I have an expression y equals 2 to the x, I can think of it as y equals e to the ln of 2 to the x power. All right, and at this point, it's almost going to solve itself. You just got to get to this moment. Because I'm going to think of this, we multiply exponents, e to the ln of 2 times x. And then the process of finding the derivative is what we were doing for all of our e stuff. dy dx. I'm going to reproduce the expression and then multiply it by something. It's a question of what that something is. In every other case, it was whatever the coefficient of x was. What's the coefficient of x here? The natural log of 2. That's the thing that's in front of x, right? So that makes it the coefficient. It's just people get bogged down with the symbolic notation here. ln of 2 doesn't look like it would be a number, but it is. It's just not a nice looking number. ln of 2, it's a number. I just don't want to write that number in front of x. I don't want to write e to the 0.693147180 That doesn't look very elegant. So we use the notation of the natural log of 2, but it's still just another number. In front of x, that makes it a coefficient, that makes it a slope. So we have our derivative here. It just doesn't look very pretty. And obviously, I think it's something that you would want to definitely check with your calculator, because not too many people get an answer like that, look at it and say, clearly that's correct. You know, it's usually one of those like, okay, I screwed something up. And so if you can have a method to check your work, it's pretty good to do that. All right, so now we just kind of want to generalize this. We want to have a rule that's going to work in all cases. So we think about what we did. Well, we didn't always work with e, right? So we have to account for both possibilities. So we have, if f of x, well, we'll first start with e. If the base is e, that's the preferred situation. So e to, some function, the power has to be something that's not just x, right? So we'll say e to the g of x power. The derivative of that would be, well, first thing we would do is reproduce whatever the expression is, right? E to the g of x. And then we got the slope of whatever that g of x is, right? Symbolically, how could we represent the slope of a function? I mean, we've been learning about it repeatedly over the last couple of weeks. What's another name for the slope of a function at a particular point? a rate of change, also known as a what's the objective or the goal for the lesson? Learn about derivatives.
Oh, that's what we're learning?
Yeah, anytime you're finding the slope of a function, you're finding that function's derivative. So I would just make a note, if I want symbolically to identify this slope, I would write g prime of x. All right, so it's the original function multiplied by the derivative of whatever the exponent is. The one thing that I need to account for is that sometimes the coefficient is variable, not variable, not 1. So I'll put like an a there, for example, to represent a constant. That would be a constant multiplier of my derivative. All right. So then you compare that to what we came up with for the base that's not e, and you could probably see how it would change into something similar, but that's something we'll talk about.